Okay, so hi everyone, and thank you for being here. It's a great pleasure for us to be on this stage. Today, Feichi and I, we're going to talk about a project we've been working on over the last few months. So let's get started. We start with a brief introduction, then we start talking about our first milestone, which is taxonomy construction, and later we go through our paper classification, paper tagging, and finally the last part is about closing. So a few words about us. My name is Daniele. Her name is Feichi. We are data scientists working for MDPI. MDPI is one of the world's largest open access publisher in the world, counting almost 2 million papers ever published in our 30 years of history, spanning through every major categories in academia, counting more than 500 journals. And I want to focus on the keywords that are provided by authors when they write their paper and they publish with us. You can well understand that the structure of a paper is title, abstract, keywords, and the full text. And I want to emphasize this part because it's central to our talk. So the same concept may appear written in very different ways. The real final goal is a sort of paper classification. We start with a scientific paper, title, abstract, and keywords to be embedded with, as we can see in a while. Then we built our 5-level taxonomy hierarchy, so spanning through domain, fields, subfield, topic, and concepts. And after we have this 5-layer taxonomy, our final goal, as mentioned, is to tag up to 10 concepts every paper in order to have a predefined and hierarchically organized concept list. So how we build our 5-level taxonomy, Feichi will introduce this in a while, but just to give you a few context before starting, we found out that existing taxonomies were a bit too coarse for our task. What we found out was that it was very useful to use what OpenAlex delivered, which is an open catalog spanning through all the scientific knowledge. And it's a CC0 license, so we could start from this. So we took advantage of their four layers, so domain, field, subfield, and topic. And our contribution was to build our 5th level and try to attach to this pyramid and having something that was tailor-made for our specific task. Just a bit more context why keywords are not taxonomy. As mentioned, the same concept, the same keyword can be written in different spellings. So we can have Industry 5.0, we can have something very related like 5th Industrial Revolution, and actually this is just a string attached to every paper. Which discipline does it belong to? From this string, it's impossible to tell. We can have Industry 5.0 connected to digital twin, edge computing, human-robot collaboration, but we still at the level we don't know. And our goal, as mentioned, is to build a hierarchy and try to have one canonical concept like Industry 5.0, which all spelling variants are merged, and to have something predefined and structured way to classify our knowledge. Why this is hard to scale? Of course, we have millions of keywords, as you can understand, millions of papers, and multiple disciplines. So if we want to use LLM, of course, or any machine learning model to classify, you can understand it's very cost and time expensive. So we cannot scale at with these numbers with a simple LLM call, for example. Science doesn't stand still, so we have also a problem about maintaining this knowledge. And lastly, sort of ambiguity, because cross-field semantics can shift in meanings, and domain experts can disagree across disciplines. We cannot have a total ground truth around it. So now, Feichi can talk about how we built our taxonomy.
Okay, great. Hello, everyone. I'm Feichi, and I'm going to introduce you about how we construct our taxonomy. And so our goal is based on the OpenAlex 4 existing layer, and then we're going to construct our 5th layer and trying to attach it to the 4th layer. And then in order to achieve this pyramid kind of taxonomy, First, we would like to compress our 2 million keywords into a concept layer. And then here you can imagine that somehow a clustering method needs to be used here. And then after we reach our concept layer, the second step is to try to attach to the OpenAlex existing taxonomy. And so basically clustering and attaching, this is two of our main steps. Okay, so first I'm going to talk about how we clustered these keywords into our concepts layer. So there are a bunch of questions to be solved here first. So the first one is, how do we deal with near duplicates? And well, this thing is a pre-processing problem, and we have to do like standardized pre-processing with normalized, deduplicate, filtering, standardized, and then there still exists some near duplicates to be dealt with. For example, the open access journal, open access material publication, these kind of, we can remove something from our existing keywords because they are overlapping with each other. And here we use Spectre 2 to first embed these keywords, and then use cosine similarity and set a very high threshold like 0.97 so that we can safely filter out those keywords which are quite near duplicates with each other. And then why we use Spectre 2 here, since it's like used all over our pipeline here, so we need to mention this because it is scientific document embedding, and it converts paper titles and abstracts into 768 dimension dense vectors, and it's based on SciBERT, which is trained on a contrastive triplet loss on 6 million citation triplets. And then mostly Spectre 2 is used for document retrieval, clustering, recommendation of papers. And here, in our case, there's a good example that, for example, Leiden, this is an algorithm for clustering. And if we use like a normal embedding strategy, it will be clustered into a Dutch city. It will be embedded into a Dutch city, but however, it's a graph clustering method. And second question here is, are all the keywords eligible to be clustered? So here we can see that there are 3 types of keywords. Some are too broad, for example, artificial intelligence, machine learning, this kind of thing is in the field level or in the subfield level. But some are too narrow. For example, bird-based uncased, which is a model version specifically, or some RNA names, which is too narrow, but we want to select the just right concepts here. So here, when we started our project, GPT-5 Mini was just released, and it was kind of expensive. So we tried to solve everything with GPT-4o Mini. And what is good with 4o Mini is that it has log props. So we know that when it's certain and when it's uncertain. And we convert log props first into a confidence score, and then we set a threshold there. If it is quite confident on a specific output, we directly output the class. For example, it's just right, and we just put maybe the just right class. And then if it's less than a confidence threshold, we use GPT-5 Mini to make the final decision. And okay, now we have our eligible keywords, but then how to cluster interdisciplinary keywords? This is another problem that we need to solve. For example, the keyword industry 5.0, it can belong to computer science, it can belong to engineering, it can also belong to social science, and this is kind of vague. So here we decide to first maybe attach the keywords first into fields and try to create some duplicates and perform per field clustering. So this is far better than global clustering, since global clustering might introduce some noises such as network, it spans computer science, biology, economics, and causing like inflated cluster size and not clear boundaries between fields. And here for field classification, we use a 2-phase LLM. And basically we find that, so because LLM is not always confident in a specific stuff. For example, we ask, so whether this, so at the first stage, we will ask the LLM whether a concept, which of the 26 OpenAlex fields do you think a concept belongs to? And then maybe it starts to try to get confused because Industry 5.0 maybe think it's somehow related to engineering and somehow related to computer science, and will both like not very certain between these two, and the same for injection drug. So at the second stage, we'll ask it again, but only give it two options. So one concept and only one field. So are you sure that this concept really belongs to this field? So at this stage, it is a easier decision for it to make. And then so here, maybe here, it will see that injection drug doesn't really belong to immunology, but more belongs to medicine. Yeah. And okay, and the fourth question is which clustering method to use. Okay, so now we go to per field clustering, and here we decide to use Leiden algorithm. So why we decide to use this? Because the resolution is possible to control. We can try to cluster larger or cluster smaller. We can choose the Leiden resolution parameter, and it is also fast and reliable for large concept graph to cluster, and it is not like other graph-based methods, so we don't need to tune a lot of parameters, and it is not very computationally heavy too, and it is very suitable for our like keyword-based task. And this is not also like a traditional feature-based clustering, because here we want to detect more like a community structure between keywords. So that's why we try to fall into the graph clustering methods. And okay, so when we decide Leiden algorithm, but now we only have a bunch of keywords there, and we now decide how to build a graph out of these keywords. So how we build a graph, here we decide again using cosine similarity to build a graph here. So we first still use Spectre 2 as our embedding tool, and embed into 768 dimensional vectors. And then we use HNSW to do a approximate nearest neighbor search to select the top k nearest neighbors for each of the keywords. And then we do a mutual KNN and try to form the edge between each keyword. And here for the edge, we do a two-phase filtering. So first, cosine similarity must be larger than a certain threshold. And then we use mutual KNN so that the graph is sparse enough, and we can perform very fast Leiden convergence on it. Okay, so all of the questions has been solved, and finally we're going to the Leiden clustering stage. And here we try to tune 3 different parameters, hyperparameters. The first is the KNN, the K from the KNN, and also the similarity minimum threshold. And the third one is a Leiden resolution, so basically how large we want our clusters to be. And here we manually created 2 data sets. First one is must link data set, and the second one is should not link. So basically, must link should be in the same cluster, should not link must stay in separate clusters. And at the right, you can see our final precision scores here. And the size of the nodes means that the number of clusters that Leiden finally gets. And here, the number is larger, so it means cluster size is smaller. And here, cluster size is larger and the number is smaller. So we don't want to be too extreme, so we try to select something good here. And finally, we decide a good must link precision with these hyperparameters. Okay. And then this is our final Leiden visualization. And actually, we have like built something here with network X and Bokeh. And you can see that this is all the clusters that we have and spanning different fields. And here for a specific cluster, you can see that this belongs to decision science. And you can see quantitative research method is a concept. And here quantitative research, yeah, somehow it's like statistical study, somehow, yes, they can be clustered into the same cluster. And here are some like more metrics so that we can really explore this cluster and try to check whether we really have the reached our concept level definition. Okay. Good. So after clustering, now we finally after clustering, now we finally can reach our concept layer. So for each cluster, we use LLM again to generate the naming, a new name for the cluster, and then the explanation, and finally form our final concept layer. Okay, so our concept layer is done here. Now we need to switch to the second step, which is attaching. So here we still have the question that do we attach directly to 4,516 topics with LLM directly? Of course not, because it's the context, the input is too large. LLM will lose accuracy for sure, and it is not also very cost efficient. So first step we do is to reduce candidates. And we use two different embeddings. One use only names, and the one use name plus explanation, and try to get the top 10 candidates for each of the embeddings for each of the concepts. So here, what is shown here are the topics that is related to this concept filtered by cosine similarity. And then secondly, we'll perform another LLM stage, which filters out not really relevant topics. For example, here for Industry 5.0, we filter out industrial technology because too broad, and the control system IoT-based is too narrow. And it can also detect, because we do a lot of prompt engineering here, it can also detect overlapping subfields. For example, advanced manufacturing, it is already belonging to the subfield industrial engineering, so there is no need for another topic in the same subfield. Okay, so finally the takeaway here is that not every problem needs an LLM. We should use the right intelligence for the right task. So basically these are our whole pipeline for constructing this taxonomy. And here for pre-processing, for graph and Leiden, for similarity, attach, and reduce candidates, here we mostly use like traditional statistical methods, but LLM can really help us improve these the accuracy of these traditional tools because it can produce more cleaner data, and LLM can also help with accurate semantic detection. Okay, so finally we want to keep our taxonomy alive too, because science is always evolving and moves fast. And here we try to create a pipeline with our infrastructure, also using prefect here, and so that we can update every quarter and about the emerging keywords emerged in our database. And you can see that the blue points here are the emerging keywords recently. This is based on the percentile rank within its fields in the last 9 months compared to the previous 5 years. So here it's last 9 months percentile rank. This is the historical percentile. And yeah, so basically here are the emerging keywords. So recently, maybe their numbers of appearance is emerging in our database. Yeah, and then the same with level, field classification, and then attaching. So we for each step we use a different prefect flow and trying to do some also manual check in between to make sure that our taxonomy is always correct and alive. Okay, so then based on this taxonomy, we have built paper tagging, and which can serve a lot of future business values. So Daniele will introduce about paper tagging.
Okay, thank you, Feichi. Now that we have this 5-layer taxonomy, our main goal was to start our second goal, so to classify our papers. Our architecture spans through a retriever, a pruning, a deterministic pruning with Python, and a re-ranker based on LLMs. So what we did was to take a scientific paper, of course, all of our scientific papers, title, abstract, and keywords. We take our 5-level hierarchy that we just built, and the stage 1 consists in a retriever, which is actually a bi-encoder approach, where we actually encode in multiple embeddings each paper and every concept that we have in our list. So we do a pairwise check based on cousin similarity. So the goal here is to reduce our potential candidates from 113K concepts to a small subset of 250. Of course, there can be some false positives, but this is the main goal here was the recall. Then since we cannot pass all of these combinations into a cross-encoder or an LLM, we wanted to prune a bit with some deterministic Python functions. And here again, we reduce the numerosity by 100 kind of potential candidates per paper. And then at this stage, we can use re-ranker in order to which is optimized for precision. So here we want to end up with the final version of the concept that are connected to each paper. So the goal is to have maximum 10 concepts per paper that can be ranked. So the first one has to be more important for that, should be the core of that paper till up to the 10th, which has something satellite talking about in that paper. And of course, they have to be hierarchically grounded. For this task, we have some GPUs that we used. For embeddings for the bi-encoder, we were using NVIDIA GeForce RTX. And for LLM, because we also self-host some models, as we can see in a while, we use an NVIDIA L40. So this problem is hard again for scaling. As we can see in a while, we are about to embed every paper on 50 embeddings. Why? Because the signal is distributed. The right concept can appear anywhere. It can appear in a keyword, in a specific part of an abstract or a title. So you can imagine that we cannot embed every paper only in a single vector, because it averages away too much the signal that we need. So we have strategy, as we can see now, up to 50 embeddings per paper. We have 2 million paper. We have 113K concepts. So we are having trillions of potential pairs to be scored. And similarity doesn't equal always correctness, because cousin gets us close, but the LLM re-ranker has to do a final step to filter out what's not needed. So this is how we built our retriever. It's a multi-view scientific retriever. It's again a bi-encoder, and we decided to have 8 complementary strategies, trying to spot in every part of our paper where that specific concept that should be important has to be retrieved. So we can have a single embedding for a title, and we take the most similar concepts, just comparing this vector for the full title. Then we have some strategies to split it. So we divide in 3 parts, and we generate several other embeddings. And we also have 3 grams of the paper, just to have a sliding window where we try to be a bit more narrow and precise to get these concepts that they are talking about. Again, something very similar on an abstract. Of course, abstract is a bit more noisy than the title, because there can be much more sentences. And we have as well here some strategies how to split the text and how to embed these splits. And of course, the keywords, that is maybe the more granular and precise thing that we have, because it's actually just a word of a few words that are very, very specific and provided already by the author. So this was very precise to embed, and we got most of our concept retrieved thanks with the keywords. So just to summarize, we have 8 methods. Each of these retrieves independently potential candidates via cosine similarity. They are merged by paper, and we can also collect some metrics that are useful to be put in as input in pruning and in re-ranker later. Just to is about the frequency. So that concept in how many methods it has been found out. The more, the better, of course, because it means that maybe this is the core concept this paper is talking about. So if we take a specific paper as an example, and we we draw here a concept map. So this is just U-mapped 2D reduction of our 768 dimensions coming from the embeddings from Spectre 2. Here you can see 4 colors, which are our 4 domains. So it's our first level of our taxonomy, and 26 labels. So these are the 26 fields belonging to each domain. So if we again try to put in this map all the concepts that have been found out from our retriever, you can see that here we can span through several and different fields and subfields. That's very good, because in a paper we cannot have, as mentioned before, we cannot have only one embedding. So the noise is distributed between several fields and subfields. And this is how we were building these 8 methods, just to have something like this. So just to try to go the more as possible into this big space that we created. Again, if we take another example, just to let you more concrete example, we can take this paper, which is talking about Industry 5.0 in digital twins in chemical industry and in IoT. Here we can see a sample of the 250 potential candidates coming from the retriever, and actually we just highlighted 3 of them. In yellow, Industry 5.0, and where this has been found out in the title. So again, we were splitting the title. We had strategies to split the abstract and the keywords, and actually Industry 5.0 has been found in the title in several sentences in the abstract and also in the keywords. Same for Industrial Internet of Things, which is actually a keyword, but as you can see in our concept list, we have Industrial Internet of Things, but these authors provided Industrial Internet of Things, parentheses, IIoT. So as mentioned before, every concept can be written in many multiple ways. We were trying to standardize in something more that we can aggregate, and we can even go further with much more advanced analytics later. And lastly, this is the hierarchy. So again, Industry 5.0, this is the topic this concept is related to, and all the hierarchy. And as you can see here, the top 3, the top 4 are all related with IoT technologies. Why? Because it's not only Industry 5.0, but it's also connected to the industry Internet of Things. So this is something we wanted to achieve, because it's semantically, it's grounded. Then the second step, so we end up with 250 potential candidates so far, and our initial goal was to reduce again before feeding them into an LLM. So the flow is to have some scope filters that filters out 100 kind of potential candidates. Here actually what we're doing was to use some Python functions that and something related with the distributions, a sort of TF-IDF styles, both on fields distributions and subfield distribution. Our distribution list is a bit skewed and skewed because we have thousands of concepts in engineering field, but few, for example, in few hundreds in dentistry. So since this is a bit skewed, we wanted to use this approach of TF-IDF. So if we see in a paper that there are many concepts, so the signal is more around dentistry, for example, so we know that this paper is more skewed on something that in our prior distribution is not. So actually we try to penalize the distributions that are less present in our corpus. Then we do something similar. We try to collapse some synonyms, so some concepts that maybe they are very similar each other in this 250 list. So we have some rules both for same name deduplication. So the goal actually here we try to use another approach. It's not semantical because we already did it in the retriever, but here actually we are trying to tokenize and see if the topic connected to each concept that is still in the bunch of potential candidates as something related with or not with the title, abstract, and keywords. So we used metrics like Jacquard to see overlapping of these tokens. So we were trying to use another approach, and actually here we were able to find out also to filter out some of them. And so both for same name, the duplication, so because a concept can have the same concept name but belongs to different topics names, or also near synonym. So we have rules also to handle this. Finally, after we have these 100 potential candidates, we built a configurable LLM pipeline for the re-ranker. So we also tested some cross-encoders, so nothing related with LLMs, but we found out after a few tests that LLMs performs better. And since we also have to tag Scilite, so Scilite is our comprehensive database maintained by our company that spans through around 190 million papers, that not only belongs to MDPI, but also from other publishers. So you can well imagine that if we have to tag all of these papers with Azure, OpenAI, or any proprietary models, it's very expensive. So we were building some pipelines where we were able to swap between only proprietary API calls, or also since we self-host some models like Qwen, for example, we wanted to test this as well in order to see if we can have some good results, and if we can wrap something around this, some architectures around self-hosted models to have something compared to paid models. So here actually we can have the goal of these LLMs are to drop, refine, dedup, and rank finally the final list. So the goal here is no matter which model and which infrastructure we're using, but to have something that tries to get the final list ever of our papers, of our concept for every papers. So we try to have something orchestrated with concurrency and batching. We are following a prefect flow. We have batches of papers. We are using async for these tasks. We try to validate with Pydantic, because every LLM output validates against through a Pydantic schema, because as you can imagine, LLMs can hallucinate, and our output format can be a bit wrong compared to what we are expecting, and in case it's going to be retried. And we have also crash safe checkpoints just to have something clear. So the last few slides, of course, since we are in our organization, we have to take care of the cost, not only about the quality. So we were testing many flagship models, but of course, as mentioned before, we have too many papers to tag. And so we were just testing and trying to focus more on Qwen and Qwen 3. When we did this task, and GPT 5.4 mini, we found out that with MDPI papers, 2 million papers, we have an estimation after our engineering around $13K US for tag 2 million papers. And for Scilite, of course, since we have around 200 million papers, we cannot use this because it can be very expensive. So we were trying our best to wrap architecture around Qwen. And what we found out was that the results were pretty good, but we wanted to have a human in the loop to evaluate these results. And so what we did was to engage some PhD experts from our company, and we provided them some papers and actually 2 models, the one from Qwen 3 stages, and the one from GPT 5.4 mini. And we're asking them to rate each concept to provide, in order to collect some metrics like precision, recalls, NDCG, and whatever, and these are the final results. So we tagged, we have more than 220 papers that with results, and we were able to have these kind of results. So again, this is Qwen 3 only, and GPT 5.4 mini, but we saw that, so this is precision at K, 1 to 10, because maximum 10 concept per paper. Of course, there is a small degradation here, the more we go down in the K, but it seems that Qwen did a great job. Also for the NDCG at K, we have good results, so the ranking seems it's quite effective. And just to close our takeaways, what's next? We found out that for our task, self-hosted can be enough. Qdrant reached results that we think it's quite impressive at the moment. Of course, we can fine-tune because we saw that few categories show lower precision and lower metrics, so of course we can have room for improvements. And of course, since it has been released not a long time ago, Qdrant 3.6, which is a mixture of expert models, we found out that especially the time has been collapsed a lot and the quality has improved a bit. So with the same pipeline, we can drop in the model swap. And what does this enable? Many analytics on top of this, as you can imagine. We can have an academic trend detection, so we can understand in advance which are the emerging topics that are emerging in academia. So the idea is to catch the demand as soon as possible, or to open a new journal or something like this. We can optimize our semantic search. We can build some recommendation system. We can optimize our journal intelligence. We can also take care of the out-of-scope control. So if a paper published or submitted is out of scope for that specific journal, and many other applications like building ontology and graph and whatever. So these are just the products as a return of the foundation that we just shared. And the final slide, the lesson learned. So we realized that we don't have to plan too far ahead, especially for tasks like this. So sometimes we were trying to predict, okay, in the next few weeks we can do this and that, but actually we made some assumptions, we tested, we discovered the better assumptions, we went back, we retested again and repeated. So this is the first lesson we learned. Another one is don't let LLM do what Python can do, because sometimes deterministic pruning before LLM can cut costs and time and not preserving quality. And the third one is finding the right tool, not the biggest tool. So we started big, but we realized that we had to reduce, to get smaller models, and because we had to take care of cost and all the metrics we just spoke just a minute before. And human evaluation, human in the loop, is not negotiable. AI is a judge, and our team expertise can be biased, but we need, and of course we have a bunch of PhDs in our organization that we wanted to take advantage of, and that's all, and thank you very much.